Welcome to Chapter 4. This is Section 4.1.1, Modeling Nonlinear Data. This is an updated version, so some of you may have this, some of you may not. So what we're going to be talking about is the relationship between the area and the radius of a disk or of a circle. So we're going to find out what happens if you double the radius, what happens to the area. So remember, the area of a circle formula, area equals pi r squared. So if our radius is 1, it's going to be pi times 1 squared. So it's going to be pi. If our radius is 2, it's going to be pi times 2 squared, which is 4 pi. Radius is 3. Pi times 3 squared, which is 9 pi. Radius is 4. Pi times 4 squared, which is 16 pi. Pi times 5 squared is 25 pi. Now when it's 10, pi times 10 squared, which is 100 pi. Pi times 15 squared is 225 pi. When the radius is 20, it's pi times 20 squared. So it's going to be 400 pi. So you can see the values at our table. And some of them are doubled, you can notice. So now the graph. What the graph would look like for our data. We would have our radius here in the x. That's our independent variable. And our area for the y, that's our dependent variable. So 1, 2, 3. So we'll go by 1s for the x. And for the area, we're going to go by 5s. 5, 10, 15, 20, 25. Now when it's 0, it's 0. 1 is 1, 2 is 4, 3 is 9, 4 is up to 16, 5 is up to 25. So our graph looks like this. Now, we would connect these dots because we could have a radius of 1.5 or 2.01. So it is a continuous function. So what this looks like is a quadratic. Now remember, it's a quadratic because it's pi times the radius squared. We're squaring that radius. That's our x. It's something like x squared, which is a quadratic when you're squaring your variable. What would the area of a circle with a radius of twice as large look like? So if the radius is twice as large, what we would do, it's not just going to double the area. Remember, area is pi r squared. So if we double our double our radius, it's pi times 2r squared. Now, when we square the 2 and the r, we have to square both. So 2 squared is 4, r squared. So the area is 4 pi r squared. We're quadrupling our area. That's just a fancy word for times 4. So we quadruple the area when we double the radius. And you can see that in our table, when our radius was 1, when we doubled it, we had 4 pi. When our radius was 2, when we doubled it, we got 16 pi. When our radius was 5, we had 25 pi. When we doubled it to 10, we got 100 pi. We quadrupled it. And then from 10 to 20, 100 times 4 is 400. Now, we can talk about our information from our graph. Now, for the lab, for our table, for the radius of a circle, the domain x has to be greater than or equal to 0. That's our radius. Our radius has to be greater than or equal to 0. Our range, our area, y has to be greater than or equal to 0. And that's because we can have a circle with a negative radius. But if we're looking just for any quadratic, our graph would look like this. So our domain would be all real numbers, and our range, y, is greater than or equal to 0. So that varies from our lab. So just in case, just keep in mind here, when we're talking about the lab, when we're talking about an actual circle, x greater than or equal to 0, because we can't have a negative radius. The radius can't be negative. Now, when we looked at our plot, our graph looked like this. So we did have an x and y-intercept. The x-intercept is at 0, 0, and that's the same spot for our y-intercept. It's also at 0, 0. So really what that's saying is that when the radius is 0, the area is 0. No radius, no circle. And that's what's going on there. Okay, we'll be talking extensively about quadratics in this chapter, and I will see you in the next video.